My project is the Smart Grid Test Facility, and I'll be giving a little taste of what we constructed, how it works. I will mention this is also through the College of Engineering, so it's a paired project. So just for some background and motivation for this project, this past summer I had the opportunity to have an internship at National Grid where I went to a lot of different sites along the power grid and got to see things like the substation where I took this very professional selfie. I waited until everyone kind of walked away and then I turned around, did it really quickly. But that's a really big transformer right behind me. On the right are some more pictures that I took while I was there. And that whole experience just kind of introduced me to power systems engineering. I became really interested in it. I think it's really cool. Also in light of climate change, I know whenever we think of how to upgrade the grid, make it more renewable, we immediately think about generation. So we think about how can we get more solar panels on the grid. But so much effort is being done right now to improve what already exists, so the aging grid infrastructure. How do we transmit power better? And that's a lot of what we focused on over the summer, and that's a lot of what my project is involved with. So I'll chat a little bit about it. I will also say I'm on a team of 5 through the College of Engineering. These are my lovely teammates, including Snoopy in the middle. There's a little dog in his pocket. We are the Power Pooches, so that's where he comes from. And so in this presentation, I'll mostly be talking about the work that I specifically did towards the project, but by the nature of a team effort, a lot of what we did was overlapping, and we helped each other out along the way. So the project objective was, like the title sounds, was to build a grid. It's an in-classroom power grid, so we needed to design and construct a device that could be used in a classroom, in a research lab, for experiments or demonstrations. So something that maybe you wheel in, something you can take out, leave in a storage facility, and it needs to be user-friendly, safe, and mobile. So how can we test different circuits and equipment in a classroom? And this objective was outlined by our customer. So in the College of Engineering, we were provided a customer who detailed what this project needed to do. And then from there, we designed it, constructed it, did all the bells and whistles on it. But he outlined what this was. And throughout this presentation, I'll be talking a little bit about the power grid on a really basic level. And so I just wanted to quickly go over those parts that I'll be talking about. And there are really only 3 main parts to a power grid, any power grid. And the first one is generation. So what makes power? So you plug your phone into the outlet. That had to come from somewhere, and it does. And it comes from things like coal plants or natural gas plants, solar farms, anything like that. Whatever makes power. And so that's really component 1 of the grid. Component 2 is how we get it places. So that's nice. You generated it in the middle of nowhere, but I need it, so can you bring it to me? That's where transmission lines come in. Transmission lines, I'm sure you've seen them. They're out, you see them, the big tall ones out on the highways, or even if you've seen small distribution lines, which are those wooden poles when you're driving on a regular road. So that's how we get power to people. And finally, the people who use it. So that's you, that's me, that's an industry. Someone who's consuming this power that we made. And these are really the 3 core components of any power grid. You'll notice as I'm going on, ours gets a little bit more detailed, but this is the core structure of any grid. I mentioned earlier that we have a customer, and we do. So he outlined the requirements, kind of like a specification sheet. This is what your project needs to do at least. It can do more, that'd be great, but this is the minimum. And so he gave us this. He just kind of plopped it down. We negotiated some of the requirements based on what we thought would be possible in the time we had. And the first 3 here align directly with the image that I showed in the previous slide. So those are the 3 core components of a power grid. We start with generation that we needed to model. So we needed at least 3 generators, which I'll talk about in a bit. And for transmission, we wanted to model what lines really do. So they are just wires, it's true, but they have specific characteristics that we call resistance, inductance, and capacitance. And we wanted to model them for real. So we needed to do a ton of calculations and figure out how they actually behave. For loads, that's typically what we call a home or industry, whatever consumes that power. We needed different types of loads because not every type of power that you consume is the same. So those are those 3 core elements I mentioned before. The 2 at the bottom weren't as explicit on the previous slide, but are there nonetheless. So for data acquisition, we take for granted, when you plug something into a wall outlet, that the power is sitting there, but you don't see it. You just hear your phone buzz and you know that it turned on and that it's charging. But in a power grid like what we built, you can't really see it. You don't really know unless we have lights on it or something like that. But we needed a way to actually monitor what was happening. So our customer requested a data acquisition system. hey, how can I probe around on your grid and see what's going on? So look at things like voltage and current. And finally, safety. That's really intrinsic to the project as a whole, kind of by the nature of an engineering project. No high voltage being exposed. We don't want to electrocute anybody. We also have a lot of moving parts that all needed to be in safety enclosures, which you'll see in a bit. I've highlighted here in periwinkle the elements that I specifically worked on. Like I said before, this really was a team effort, so a lot of what we did was overlapping. But these elements I was pretty primarily responsible for. So I'll chat a bit about generation, how we set that up, how we transmitted that power, and towards the end we all kind of jumped in on safety, making sure nothing was exposed. We did blow lots of things up, but we all turned out okay. So we're going to start with generation. So like I said, what makes power? So this could be a coal plant, solar farm, wind farm, and we needed to model that, and we needed 3 models of that, and we needed to put them together. So as much as I would love to build a huge power plant, that was not feasible, so we needed to model it. And the way that we did that was through combining some machines. So we took a motor, combined it with a belt over its shaft to an alternator. And end of the day, what this does, it generates power at 60 hertz. That's really it. So that was our way of modeling it, and we had 2 sets of these, so 2 generators like this. And like I said before, we needed 3. And at first we decided we couldn't do all 3 like this because of financial restrictions on our budget, and we needed a different type for the 3rd, but it ended up turning out really, really well because our 3rd one is a reference. So it's straight from the wall. We use it as our, like I said, our reference. It's like the perfect, beautiful sine wave, and we get to match ours to that. So it ended up being a very good financial restriction. So I'm going to talk a little bit about stability. This is something that I was really responsible for in the project and was really important to me. It was really the bulk of my technical work. So I keep referencing the wall outlet. When you plug something in, you're pretty much getting something at 60 hertz, and we take it for granted that it's there. But when I build something, you have no idea what frequency it's at, and I don't either. We can't trust that. So we need to make sure it's stable. And what happens is as you change things along the rest of the grid network, frequency changes, unfortunately. But we needed to build a way to make sure it stayed constant, or at least close enough. And the way that we do that is through a feedback loop. Feedback you may have heard of in terms of biological processes. They're really kind of a phenomenon throughout a lot of different fields. But this is a block diagram. We use these a lot in engineering. I'm going to go into how it works. But the idea is you want a feedback loop that's continuously running and making sure something is stable. That's really it. And when we were designing this, the way that we think about these things is how components talk to each other, which may seem strange, but when I was designing the system, I said, okay, I'm going to have this alternator, and I want it to tell this information to something else. And that's really how we think about these signals. And for me, that's the easiest way I understand it, so that's how we're going to do it. So we're going to just kind of walk through the feedback loop and how it's running. And the way it starts is through this, in the bottom left corner, there's a microcontroller, which you may have heard of. They're just like a little computer that you can program yourself. So it thinks however you want it to think. And what I told it to say is, hey, what's the alternator's frequency? And I wanted it to ask because our main goal here is to keep the frequency at 60 hertz. So let's check. Let's make sure it's like close. Well, the rotary encoder has access to that, so it's going to ask. And a really excited alternator is going to tell you it's at 55 hertz or whatever it is. The rotary encoder will relay that information back. And the microcontroller is the one with the brain, so it doesn't just say things like the other ones do, but it can think. It says, hey, that's too low, frequency's below 60 hertz, I need to bump it back up. And it does that by communicating to the motor driver, which closes in the loop. So now we have a full loop that's running, and the cycle starts again. So over and over and over, the microcontroller is asking, what's your frequency, what's your frequency, what's your frequency? And as the output goes up and down, it keeps it centered around 60 hertz. So the idea is that yellow box on the right, the remainder of grid network, as you change things going on there, frequency will naturally change. But this system ensures that it will stay centered around 60 hertz, even as that happens. That's the idea. And this is what that looks like. Our project is on a cart, I should have mentioned. It is mobile. And so I highlighted here 3 boxes of those main components. The motor and alternator are in an enclosure in the bottom, and they loop back up to the brain is that little red block, our microcontroller, and then the motor driver is up top. So this is kind of the real live version of what that block diagram looked like. So instead of them, verbally saying, what's your frequency, they're propagated through signals, so electrical signals is how we built it. Another part that I'll talk about briefly is synchronization. So like I said before, we need 3 generators, which is nice and dandy and all, but can we just plug them in together? No, don't do that. I've tried. The idea here is, all right, let's say we have 2 generators. I have this coal plant. It's lovely, but it's a pollutant. That's okay. And it's on the grid. It's already producing power. And I build a solar farm, and I want to plug it into the grid. So I look at, these are my waveforms for power flow. And oh my gosh, they look so similar. I can probably just plug this in. It's going to be fine. My frequency's the same. My magnitude's the same. It's going to be great. But then I notice a really subtle difference and a really important difference. And that's that the peaks and the troughs of the waveforms don't line up. And that's really important because if I plug them in, bad things will happen, and I can promise that. So what we call this is out of phase. They have a different phase on their waveform. And we needed a way to make them in phase before we could plug them in without blowing more things up. So the way that we decided to do this was a fairly common method on a large scale even. And it's basically using a light bulb. So it looked pretty, so I was all in favor of it. And the idea is you put a little bulb between the waveforms, and it'll see the combination of them. And so as a result, you can see, as the light fades in and out, what the phase looks like. So in the top one, they're super out of phase, like we saw before. There's a voltage potential, and current can flow. The light's on. Opposite thing when the light's off. So this is what those look like. That's the little LED. And basically, when you see the light is at its dimmest, you know that they are completely in phase. There's no potential, and you plug it in. That's how you plug in your solar plant. So these work great. I love them dearly. I call them sync circuits. I think they're adorable. And I'll talk briefly about transmission lines. I was sort of a secondary help on transmission. A teammate of mine was really the primary contributor, but we designed them together. So basically, we made like I said before, we wanted to model real live transmission lines, so what they really do. That was a customer requirement. We were really excited to do that. These are printed circuit boards on the bottom that we designed. We populated with all those parts on them, and basically they do, like I said, so they have all those different electrical characteristics that a real model transmission line would do. I wanted to show some pictures of the construction of the project because it was a very interesting process. We started with a mock-up, so that's this like cardboard version of my project. And this was at the very beginning of the year when we were told, you know, what is it going to look like? Build me a sample. And it was interesting to see a lot of things that ended up being the same and a lot of things that were very different. We also had a Shark Tank night, which is on the bottom right. We had to pitch our project to a bunch of alumni, and we won somehow. So started the year off well. Here's some more pictures of construction. This picture on the left is right after I cleaned up the whole project. We had wires, like literally, like we took every wire in the lab. We had all of them. And I was like, you know, this is too messy, and I went to clean everything. I spent at least 20 minutes cleaning, and that was the result. I was very proud. On the right are some other things that we had going along the way. On the bottom, you can see those little donut-looking things. They're called inductors. I hand wound them all. In the middle is some CAD modeling that I did for a very professional Power Pooches sign. It was super necessary. And the final product, like I said, is on a cart. So this is sort of the front of the cart. We've since upgraded some labels and things like that. But the idea is that the high voltage moving parts are on the bottom and safety enclosures. The middle layer is that feedback loop that I showed you before. And the top is like a plug and play. So that's where we have Velcro. Everything we have on there is Velcro, so you can kind of plug in what you want to study and take out what you don't want to study. So you can interchange loads, you can change all different types of things on the grid. We've been kind of just having too much fun the past couple weeks plugging in all of our own stuff, seeing what it does. Here are just some kind of better images of the front and the back. Lots of things going on there, but we've tried to organize it. There's our Power Pooch. I 3D printed that. Also super necessary. So overall, I had a really awesome time working on this project. I learned so much over the summer, and I also got to learn a lot here, not only through working on it, but through my teammates and through the faculty who helped us out. So big thanks to everyone who helped us along the way. We had lots of support, and I had an awesome time. So thank you.